Okay, so this is the second video on relations. So in the first video, we looked at what it means to be a relation, to be reflexive, to be symmetric, to be transitive. In this video, we're going to focus on equivalence relations and equivalence classes. So first we need the definition. A relation R on A that is reflexive, symmetric, and transitive is called an equivalence relation. So if it has all three of those properties, it is an equivalence relation. In the last video, we only had one example that was an equivalence relation, and that was the relation x equals y. Okay, because it was reflexive, because x does equal itself for every single real number x, if x equals y, then y equals x was true, so we are symmetric. And then if x equals y and y equals z, then x equals z, so it is transitive. So that's an example of an equivalence relation. It's kind of the most boring, the most simplistic, not super useful equivalence relations. So we want to look at some more things. Some are going to be equivalence relations, some aren't. Okay. So let's go ahead and take an example. I don't remember what example number we're on. Let's go with, I think we're on example 5. Okay. And we are going to let R be a subset of natural numbers squared, of n squared. So my relation is on the natural numbers. We are going to define x, r, y. So x is related to y. I'm going to define that by x divides y. Okay, if you don't remember what that little slash means, that means x divides into y, or y equals x times some integer, in our case natural number, because that's our universe, n. Okay, so we want to prove or disprove R is an equivalence relation. Okay, so I need to check it for reflexive, symmetric, transitive. So first we do some scratch work off to the side. So let's say, so first I need to check reflexive, x divides x. So does x divide into itself? Yes, that's okay, because x does equal x times 1. Okay. Symmetric. Assume x divides y. Am I going to get y divides x? So is that going to imply y divides x? Well, that should jump out at you as kind of funny, right? Because I know 3 divides 6, but 6 does not divide 3. Okay, so at this point, I can answer the question, prove or disprove R is an equivalence relation. We have a counterexample. So, I could say, counterexample. Okay. So here we say 3 is related to 6, but 6 is not related to 3. So R is not symmetric, and therefore not an equivalence relation. And that's all you need to show that this is not an equivalence relation. Now I do want to show you how to prove, okay, just because we haven't done a formal proof, I want to give a formal proof that this R is transitive. So that's what we're going to do. We're going to prove that R is transitive. Okay, so the only thing it failed was symmetric. All right. First, we're going to do some scratch work. Almost all your proofs will start with scratch work. So for transitive, I'm going to assume x divides y and y divides z, right? That's what transitive says. Get that matching middle piece. And my goal is x divides z. Okay, here we go. So x divides y. That means y equals x times some natural number n. Y divides z means z equals y times some natural number m. But my goal is to get z equal to x times some natural number. I don't care what it is as long as it's a natural number. Well, maybe you see it already, but I'm going to take what y equals and substitute it in here. So we get z equals x times n times m. And that is what we want. So now we can write up a formal proof, okay, that R is transitive. So here we go. Proof. So we got to put all our front matter. Let R subset of n squared be defined by x r y if and only if x divides y. Okay. Now we can start on what we want. So we want to show transitive, so we assume there exist x, y, and z in the natural numbers such that x is related to y and y is related to z. So there I'm just stating my hypothesis part for transitive. I have to assume those two facts. Okay. Then x divides y and y divides z. That's the definition of R, so we're good. Okay. This means there exist m and n in the natural numbers with, what did we say? We said y equals xn and z equals ym. Thus, z equals x times nm. And we're doing a very, very formal proof here, okay? Most teachers, you wouldn't need to put quite this much detail. Since nm, right, that product is an element of the natural numbers, because a natural number times a natural number is still going to be a natural number. Nm is an element of natural numbers, x divides z. Thus, x is related to z. So that's what a proof for transitive looks like. Okay. Here I assumed what I need to. X is related to y and y is related to z, and worked until I got x related to z. Okay. All right. But this is not an equivalence relation because it failed symmetric, but it is transitive. Let's definitely look at more examples. Okay, so this next one, example 6, I believe, we are going to say x, sy, if and only if x is congruent to y mod 3. And I need to give us a universe. Let's say we're in z squared. Okay. All right. So we're just dealing with integers. You may not have seen modulo numbers before, so let me explain what this means. There are 3 different ways to think about this. Okay. First way, x is congruent to y mod 3 means, so the first way, x and y have the same remainder when divided by 3. And that is the most intuitive way to think about it. So an example would be, I don't know, 12 and 36 both have remainder 0 when divided by 3. So 12 would be congruent to 36, mod 3. Okay. 13 and 37 both have remainder 1 when divided by 3. So they would both be congruent, mod 3. Another way to think about this, okay, you could say x and y have same form, and there are 3 different possible forms when you divide by 3. They can be 3 times a number, that'd be remainder 0, or they can be 3 times a number plus 1, because that's remainder 1, or 3 times number plus 2, because that's remainder 2. So congruent mod 3 means they have the same form. The other way to think about this, and this is the technical definition, which is what we're going to use in our proofs, is that if x is congruent to y mod 3, that means 3 divides x minus y. So let's take a second and look and see if we understand what these are saying before we get into showing this is an equivalence relation. All right, so let's take 2 numbers that have the same remainder when divided by 3. So for example, 4 and 19, okay? So 4 and 19, they both have remainder 1 when you divide by 3. So that's the first one. They have the same remainder when divided by 3. Now the second meaning, since they have remainder 1, they're both going to be of this form, 3n plus 1. Let's look at that. So that would be, let's see, 3 times 1 plus 1, that would be 4, and 3 times 6 plus 1, that would be 19. So we can see they are of that same form. This even works for negative numbers. For example, negative 5. It's weird when you think remainder, but negative 5 is of the form 3 times negative 2 plus 1. So it would also be congruent to these modulo 3. All right. Now let's look at this last meaning, the one we're going to use. So this says 3 should divide when I subtract them. Well, what is 4 minus 19? That's negative 15. That's definitely divisible by 3. Let's put the negative 5 in there. What if I do 4 minus negative 5? I get 9. That's definitely divisible by 3. Okay, same thing if you take the 19 and the negative 5. You'll get something divisible by 3. So these 3 green statements, they are all the same thing. We are going to use, because it's the easiest to use in proofs, that third one, 3 divides x minus y. And this would be true any modulo you see. If it says x congruent to y mod 13, that would mean 13 divides x minus y. That's how modulo works. Okay. So that was a very, very brief course in modular arithmetic. Now we want to prove S is an equivalence relation. Okay, better do our scratch work first. All right, so reflexive. I need any integer I pick needs to be related to itself. Well, that means we need x congruent to x mod 3. That means we need 3 to divide x minus x, which means we need 3 to divide 0. That looks funny, but that actually is true, okay? Because 0 does equal 3 times 0. So that actually is okay. So yes, it is reflexive. A number is going to be congruent to itself, mod 3. All right, let's look at symmetric. So if x is related to y, that means x is congruent to y mod 3. All right, well that means 3 divides x minus y. But that's the same thing as saying that x minus y equals 3 times some integer. But look at this, if I switch to get y minus x, because I'm wanting to switch the order, then that's just 3 times negative of that integer. Multiply both sides by -1, and we get that, which means 3 divides y minus x, which means y is congruent to x, mod 3. So we are symmetric. That's good, because we're supposed to get it's an equivalence relation. All right, now let me do transitive over here, and then we'll write up our proof. So transitive, we are going to assume x is related to y, and y is related to z. Now intuitively, using that very, very first green definition, this makes sense. If x and y have the same remainder when divided by 3, and y and z have the same remainder when divided by 3, then x and z have the same remainder when divided by 3. But we want to be more rigorous than that, so we're going to use our definition. So this means x congruent to y mod 3 and y congruent to z mod 3. And I can't fit it all in, but you get it. Blah, 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 mod 3. Okay, so that means 3 divides x minus y, and 3 divides y minus z. That means x minus y equals 3 times something, and y minus z equals 3 times something. But look at that, if I add these together, so I'm going to do x minus y plus y minus z. Okay, that's going to give me x minus z, and that's going to be 3n plus 3m, but that's just 3m plus m. So 3 does divide x minus z, which means x is congruent to z mod 3. Okay, which is what I wanted, because that gives me x related to z. So now I have my scratch work. I see how my proof should go. That I just set aside, and then I write up my proof to turn into my teacher. Okay. So proof. Going to let S be a subset of Z squared. We said that was our universe. Be defined by X, S, Y, if and only if X is congruent to Y mod 3. Okay. Now we will work on reflexive. So reflexive starts with a for every statement in its definition. So that means I need to take an arbitrary integer. So we're going to let, I'm going to use A be an element of the integers. Then, now I'm going back to my scratch work. I am going to start with what I know is true and then work my way up, okay, to get to reflexive. So that's what I'm doing here. I'm working backwards. Then 0 equals A times 0 is obviously true. So we have A divides 0. Oops, sorry. What did I do? Brain fart moment. I need a 3 there, not an A. That's what happens when I can't see my scratch work while I'm writing. Easy fix. So then 0 equals 3 times 0 is obviously true. So we have 3 divides 0, meaning 3 divides A minus A. So A is congruent to A mod 3. Ergo A, S, A. So we have reflexive. We took an arbitrary element from my set and showed it has to be related to itself. Symmetric. Now we're going to let X and Y be elements of Z with X related to Y. And now I'm going to use my scratch work. Then X is congruent to Y. In fact, we'll do this shorthand way, right? Be lazy mathematicians, like good mathematicians. Then X is congruent to Y. Mod 3 means 3 divides X minus Y means X minus Y equals 3n for some n in the natural numbers. Then we get Y minus X equals 3 times negative n. Okay. Since negative n is an element of Z, oh yeah, should have put Z here. Man, I'm having a day. Okay. Since negative n is an element of Z, means 3 divides Y minus X. Thus, Y is congruent to X mod 3. So YSX, and that's the whole point of symmetric, is start with X related to Y and end up with Y related to X. Okay. See if I can do transitive without a silly mistake. transitive. So here, I need to let x, y, and z be integers with x related to y and y related to z. Then x is congruent to y mod 3 and y is congruent to z mod 3. So there exist integers m and n such that x minus y equals 3n and y minus z equals 3m. Notice here I skipped over the 3 divides x minus y and 3 divides y minus z. It just depends on your teacher as to how many steps you can skip, but this gets a little redundant to keep saying that over and over, so I did skip that step. Okay. Thus, here we go. X minus z is the same thing as x minus y plus y minus z is the same thing as 3n plus 3m is the same thing as 3n plus m. Since n plus m is an integer, 3 divides x minus z, meaning x is congruent to z mod 3. Ergo, x related to z. And that's what we needed for transitive. So then we'll put our 3 dots. These mean therefore. Therefore, S is an equivalence relation. Okay, so that's how a proof looks for equivalence relation. You just show each of the 3 pieces. Sometimes they're fairly straightforward, sometimes they take more work. Okay. Now we need to look at something else that's very, very closely related. So we want to look at something called an equivalence class. Okay. So again, we're going to let R be a relation on A. So the equivalence class of little a, an element of big A, is, here we go. So we put square brackets around little a. That means equivalence class. That's just the notation for it. But it's going to be the set of all x such that x is related to A. Okay. Now, we want this to have symmetry, so I left out a word here. This needs to be an equivalence relation. Okay? Otherwise, equivalence class doesn't make sense. So R has to be an equivalence relation. That means if x is related to A, I have symmetry, so A is related to x. So some definitions will list this second way, but it means the same thing because one implies the other because you're guaranteed symmetry because you're an equivalence relation. Okay, so let's see an example of this. So if I look back at example 6, and I want the equivalence class of 1, That's going to be everything that's related to 1. So that means everything that is congruent to 1 mod 3. Well, that means everything that has a remainder 1 when divided by 3. So the equivalence class of 1 is going to contain stuff like we saw, like -5 and 4 and 19. Stuff like that all has remainder 1 when divided by 3. Okay. In fact, we already said the form these things have to have. We already said those are going to be things of the form 3m plus 1. We actually already made that connection. Okay. It's not always easy to get a form for an equivalence class, but this one has a nice form. So for 1, it's everything with remainder 1 when divided by 3. If I want 0, that's going to be things that have remainder 0, but that just means multiples of 3. So I could write the set, and this is the best way to write it, like this. It's all the multiples of 3 are related to 0 because they have remainder 0 when divided by 3. I could try to list just so you could get an idea. Right? So it's things like that. Okay? Then the equivalence class of 2 is going to be everything that has a remainder 2 when divided by 3. Okay. These equivalence classes actually do cover every single possible number. So you take, I don't know, 26. You go, that has remainder 2 when divided by 3. So it's going to be related to 2. So it's going to be in that equivalence class. Now, one thing we want to be careful about is we want, if A and B are related to each other, we want them to have the same exact equivalence class. So let's go ahead and prove that, okay, in general. So here's a theorem. We need to let R be an equivalence relation on A. Then, here we go. Here's what we want to prove. Equivalence class of A equals the equivalence class of B if and only if A is related to B. Okay, so here we go. Let's prove that. So let's go ahead and do this direction first. So I'm going to assume equivalence class of A equals equivalence class of B. All right, here we go. Now remember, R is an equivalence relation. That means R is reflexive. So since R is reflexive, A is related to itself. Okay, that means by definition of the equivalence class of A is an element of its own equivalence class. But we just said A and B have the same equivalence class. So that means, which means A is in the equivalence class of B. Because those two sets are equal, they have the exact same elements. Okay, but what does it mean to be in the equivalence class? The actual definition was all things that are related to B. So by definition, means we have A related to B. Which, look, that's exactly what we wanted to prove. That was the conclusion we wanted. So we've shown one direction. That's the easier direction. Neither direction's too bad, though. Okay, so let's go the other way. Now we are going to assume A is related to B. Okay, And I want to show that they have these same equivalence classes. So we're going to do this by showing set containment two ways. Okay. So first, we will let X be an element of the equivalence class of A. All right, and we want to show that X is in the equivalence class of B. Then X is related to A. That's what it means to be in the equivalence class. But what did we assume? We assumed A is related to B. So, but A is related to B. So by transitivity, well, what does transitive say? If I have X related to A related to B, I can collapse down that middle and get X related to B. So by transitivity, X is related to B. But that is what it means to be in the equivalence class. That's how we define the equivalence class. So X is in the equivalence class of B. What we have shown thus far, okay, so ergo, we showed the equivalence class of A is a subset of the equivalence class of B. Everything in A's equivalence class is also in B's equivalence class. Now I need to go the other direction. So I need to let X be in the equivalence class of B. Well, by definition, that means X is related to B. Okay. But, so I assumed A is related to B, but remember, R is an equivalence relation. That means it's symmetric. So, B is related to A by symmetry. So, by transitivity, X is related to A. So that we had to use both symmetry to get the A and B in the correct order, so they would match up with the X related to B, to use transitivity to get X related to A. All right, but that's what it means to be in the equivalence class of A. Thus, X is in the equivalence class of A. So we just showed the equivalence class of B is a subset of the equivalence class of A. But wait, if A is a subset, if one set is a subset of another, and vice versa, so if equivalence class of A is subset of equivalence class of B, and equivalence class of B is subset of equivalence class of A, that means they're equal. So therefore, equivalence class of A equals equivalence class of B. And that's what our proof wanted. Okay, we showed both directions, so we're done. Okay, what this theorem is showing you, what this proof is showing you, is that equivalence classes, you can pick any representative you want. So let's think back to our modulo 3 equivalence classes. So when I said equivalence class of 0 equals the set of all multiples of 3, I could also have said the equivalence class of, I don't know, negative 24 equals the set of all multiples of 3. Because they both have remainder 0 when divided by 3, that means their equivalence classes are identical. They're the same. It doesn't matter which number I choose to represent the class. I'm getting the exact same set either way. If I take everything related to negative 24, I get the same thing as if I took everything related to 0. That's what that theorem says. So basically what example 6 did was it took all the integers and divided them into 3 groups. Every integer either has remainder 0, 1, or 2 when divided by 3. In fact, 0, 1, and 2 are in those. But 3, 4, 5, 6, 7, 8, 9, 10, 11, and on and on. And you can go into the negatives too. You would have, let's see, -1, -2, -3, and so on. So basically we have split the integers into 3 different classes, equivalence classes. Another word for this is partition. I split it into 3 sets that cover everything, but they have nothing in common. They don't overlap at all. Okay, so I want to do one more example that's a little fancier, and then we'll call it good enough. So example 7. We are going to be in the real numbers. So we're going to let our relation be R, and it'll be subset of R2. So we're in the real numbers. And here's our definition. We're going to say X is related to Y if and only if sine of X equals sine of Y. Okay, so let's think of an example pair that are related. So for example, we could say that sine of 0 is the same thing as sine at pi. So we would say that 0 is related to pi because they both output 0 when plugged into sine. That's what this relation means. Okay. So I'm just going to outline the proof that this is actually an equivalence relation because it's a really nice proof. It's actually shorter than the last one we did. So proof, we're going to assume all that front matter. And let's do reflexive. Okay, so we need to take an arbitrary real number, x be an element of the real numbers. Well, then sine of x equals sine of x. That's kind of duh. All right, so x is related to itself. Symmetric. Let x and y be real numbers with x related to y. All right, again, we're doing an outline here. So that means sine of x equals sine of y. That's just what this particular relation says. It means to be related. Well, that's the same thing as sine of y equals sine of x, which is the same thing as saying y is related to x. We like equal signs because you can just switch the two sides. We like plus signs and multiplication because you can just switch, okay? And that makes symmetric easier. All right. Transitive. We need to let x, y, and z be real numbers with x related to y and y related to z. All right. So here we go. We have sine of x equals sine of y, and we get sine of y equals sine of z. That's just what it means to be related according to this relation. But wait, sine of y is what it is. So that means sine of x equals sine of z. They equal the same thing. They must equal each other, which means x is related to z. So we get transitive. So that's an outline of the proof. It's just missing a couple words to make complete sentences. Okay, but this is an equivalence relation. Everything is related to itself. If two things are related one direction, then I can reverse them and they're still related. And then I get transitivity, that whole collapse the middle. Okay. Now, what I really want to look at with this guy, because the proof wasn't too bad, are the equivalence classes. Because here's where we can get a nice view of equivalence classes. So let's start easy, and look at the equivalence class of pi over 2. All right, so anything is going to be related if sine of x is the same as sine of pi over 2. But what is sine of pi over 2? That's 1. In fact, if you think of your unit circle, I can't draw a circle, but go with me. We're talking about up here, okay? That's where sine is 1. And that's the only spot on the unit circle where sine is 1. So at pi over 2 it works, but then if I travel all the way around, so add 2 pi, I'm back there again. Or if I travel the other direction and subtract 2 pi, I'm back again. So that means the things that are equivalent to this, that give me that same value, are going to be things like pi over 2 plus 2 pi, or pi over 2 minus 2 pi, or pi over 2, I don't know, plus 10 pi, because I would have gone around the circle 5 times, right? Pi over 2 minus 16 pi, I would have gone around the circle the other direction 8 times. So we can write this nicely. We can say that the equivalence class of pi over 2 is going to be all things of the form pi over 2 plus 2k pi, such that k is an integer. And so that takes care of the type of things I was listing, right? If k is negative 8, I get the minus 16 pi. If k is 5, I get the 10 pi. Okay. So this is the equivalence class of pi over 2. I could also have said this is the equivalence class of, I don't know, 5 pi over 2, because that's one of the elements in this thing, okay? So that equals the same thing. Doesn't matter which element of it I take, they all have the same equivalence class, because they all have sine of that thing equals 1. Okay, but these can get a little more complicated. So let's look at just one. That's not too bad, but a little more complicated. Let's look at the equivalence class of pi over 4. So I need sine of x to equal sine of pi over 4, which is square root of 2 over 2. Or if you prefer, you could say 1 over root 2. I don't care. Same thing. Okay. If you think about your unit circle, let me draw it again. This actually happens at 2 spots. It does happen at pi over 4, but it also happens out here at 3 pi over 4. So that makes this more interesting. So if I start at pi over 4 and go around the circle one way or another, I'll do plus 2 pi or minus 2 pi over and over. I'll get the value. But if I start at 3 pi over 4, I can also go around the circle 2 pi and still get back where I started. So this equivalence class, okay, is going to be the set of all x such that x equals, it's either going to be pi over 4 plus 2k pi, or, I'm running out of room, x equals 3 pi over 4 plus 2k pi, for k an element of the integers. So basically I'm saying either it matched with pi over 4, maybe going around the circle a bunch of times, or it matched with 3 pi over 4, maybe going around the circle a bunch of times. Either way, I'm getting the same value for sine, so it's related to pi over 4. So that's how equivalence classes work. Notice with the modulo 3, we only had 3 equivalence classes, because you're either remainder 0, 1, or 2 when divided by 3. Here I'm getting infinitely many equivalence classes, okay? In fact, every point from negative pi over 2 to pi over 2, that's going to give me a different sign value. And so those are going to be my infinitely many equivalence classes. Okay, every single angle value from negative pi over 2 all the way up to pi over 2 will give me another equivalence class. So that is the idea of equivalence relations and equivalence classes. Hopefully that's enough of a crash course that you have an idea of how they work, have a feel for how they work. So you are always welcome to email me if you have any specific questions about this. I hope it helped.